All right, let's make a start. Thank you all for coming. I know that this week is technically dead week, but I wasn't able to be here last week, and I really wanted to be able to give you the final lecture, so that's why I figured I would move it today. Technically, it's allowed, because a large portion of today's lecture is, in fact, review, so on that basis, I'm not breaking the rules too much. Okay, so today is the deadline for all work associated with the class. So assignment 5 is due today. You can hand it in at the front, as you can see, or you can hand it in by 5 o'clock in the mailbox room, as usual. Also, as promised, I have a box here of Berkeley Seismolab mugs. So those of you who have been running the MyShake app for us on your Android phone, please come down at the end, and I will be happy to give you a Berkeley Seismolab mug. It's not too late. You have until the end of the lecture to put the new version of the app. Please, if you did download it sort of 2 weeks ago, please update the version of the app you have. The new version of the app, you can get it either from the Google Play Store or from the earthquakes.berkeley.edu/MyShake webpage. Whichever way you got it the first time, you can get a new version. So please download the new version. The new version has no impact on you whatsoever, but it actually provides us with some additional important data. So it's really, really helpful for us if you can download the new version of the app. So again, now's your chance. You have an hour to put the app on your phone. Chinkai is here. So if you have any problems downloading the app, he'll be happy to help you, and then you can get your Berkeley Seismolab mug. Okay. I feel like I should go on NPR or PBS or whatever. Okay, some announcements before we move into today's lecture. I already told you that the assignment 5 is due by 5 p.m. today. I think you all know when the final exam is. It's on Wednesday, December the 17th. It's a 2-hour exam. It's in 150 Wheeler. Oops, it's supposed to say Wheeler Hall. Sorry, I didn't delete the gym part. That was last year's location. Okay, the structure of the final exam. There are 2 parts to the final exam. The first part is essentially exactly what you've seen twice already. So think of it as being midterm number 3. So it's exactly the same structure as the 2 midterms you've already had, and it will be on the final third of the class, i.e. everything that we've covered since the second midterm. And then the second part is the synthesis part. It's the final part, if you like, and that will be on all material in the class, and we'll try to draw what we've learned across the whole class. So I'm sort of saying 1 hour for each of these. We will just give you one exam booklet at the beginning of at 8 o'clock, and you will have 2 hours to complete the exam. Okay? Any questions about the final exam? Yeah. So that's right. So yes, thank you. I didn't say that. So the structure of this part is slightly different. There will be 30 multiple choice questions, and then you'll be asked to answer 2 of 3 short answer questions rather than 1 of 2. And that also means there'll be no true false. That's right. So it's a slightly different structure to the midterms. Yeah, thank you. Yeah. Yeah, this is all. So there's 30% available for the final, and that's the whole thing here. Yeah, yeah. Yeah. Do you have like a what? No, you don't need to bring a Scantron, you don't need to bring a grey book. It's kind of the same as we've done in the midterms. You'll have an answer sheet, and you just need a pen and paper, and whatever other implements you've used to do any of the assignments, calculator, ruler, whatever it's the same rules, same guidelines, whatever as for the midterms. Any other questions? Okay. There will also be a final review. That will be on Sunday, this coming Sunday, at 3 to 6 p.m. in Evans 10. Come at 3. It'll be the same drill as the review sessions that you had for the midterms. You should come with your questions, and the GSIs will answer your questions, and they'll do that until they've answered all the questions or until 6 p.m., whichever comes first. Okay? So the other thing, so that you guys know, the GSIs are holding their regular office hours this week, but next week we will all be away at a meeting. So we will not be on campus, except obviously for the final exam. So really this week is the time to ask the questions that you have, attend the review session. They put the review session as close to the exam as they possibly could, but then on Monday and Tuesday of next week, we will all be away at this meeting, and then we'll just be back here on Wednesday morning for the exam, just so that you're aware of that. Okay? Any other questions, logistical questions, before we move into today's class? Great. All right, so today is really the class wrap-up. It's sort of part review and partly what is your charge? What's your responsibility over the coming decades? Now that you are sort of earthquake-educated individuals, what's your responsibility when it comes to reducing the impacts of future earthquakes? So that's really what I want to cover. But before I give you my take on what this class was about, I'd like to hear from you on what you think this class was about, what you think are the most important things that you will take away from the class. Yeah. Okay, so the possible hazards and risks and how to reduce the damage. Anything else? Specifics? Yay! Animals can't predict earthquakes. That's obviously exactly right. I probably told you this, but I have not yet given a public talk when I have not been asked if animals can predict earthquakes. So yes, if everybody can take away from this class that animals cannot predict earthquakes, that will be a success. What else? Nothing else. Nothing else anybody's taking away. Yeah.
How you can prepare for earthquakes.
Okay, the things, the red flags. Right, so how to prepare for earthquakes, and then when you're buying a house or moving into an apartment, what are the red flags to look for? And some examples of red flags? Yeah. Soft-story buildings. As you start to think about where you're going to live next year, soft-story buildings is a key one. Yeah. Okay, what year the building was made. What are the 2 key years to know? Say it again. Right, 1973 and 1997 are the 2 key years. Big changes in building codes in those 2 years, so you want to look for buildings built after one of those 2 dates, preferably the later date, of course, but that's the challenge. What else? Yeah. Bricks are not a good place to be. Anything else? Okay, so you've all listed the practical takeaway message, which is great. I'm not criticizing that for a moment, but none of you have mentioned the science. Any cool science to take away from this class? Yes? Okay, so the beach ball diagrams, the moment tensors, and how they can tell you the difference between explosive sources and the different types of earthquake sources. Anything else? Yeah. Elastic rebound theory. Obviously, that's the key theory that is sort of at the heart of our understanding of the earthquakes process. Okay, one more, and I'll give you a break. Yeah. Wow. Pyroclastic is very specific. Pyroclastic flows are very fast, and you are not going to be able to outrun them. That is another key fact. Unlike, for example, of course, the lava flow in Hawaii, which I don't know if any of you have been monitoring, it did, in fact, go through that town that we were looking at. If you remember, it was just approaching the town when we were talking about it. It went through the town. It destroyed a few people's homes. It continued down the hill, got to the road, well, not the road in front of the houses, but the main circum-Hawaii road. But in fact, it then stopped. It didn't go and cover the road, which would have been a major source of difficulty for people living on the island. At that point, completely by chance, by luck, there was a breakout, what they call a breakout, where the flow broke out from one of its tunnels much higher up in the volcano and started another path coming down the side of the volcano. Okay, all right, so that's great. I mean, yeah, what you described, I think, covers a lot of the class. So here's my recap of the class as a whole. We started off by talking about historic lessons, okay, looking to what's happened in the past to tell us about the future. And of course, the key past earthquakes that we talked about were, first of all, the 1868 earthquake, which was on the Hayward Fault, south of here, just south of here, and was called the Great San Francisco Earthquake because of the damage that it did to the city of San Francisco. Of course, then in 1906, we had another even bigger earthquake, which was the new Great San Francisco Earthquake, and of course destroyed much of the city of San Francisco. Obviously, there's a repeating cycle here. And then more recently, the significant earthquakes were 1989, the Loma Prieta earthquake. In fact, all of these photos come from the Loma Prieta earthquake. This is the, what's it called? The Marina District, the Marina District, where there are a lot of soft-story buildings, plus the fact that it was man-made land, and so the amplification factor was more significant. The collapse of the Nimitz Expressway, that's in fact what you're seeing in both of these pictures, these columns that collapsed, that's where a large fraction of the fatalities were, and then some more of the soft-story buildings that collapsed. This is the level where the garages were that collapsed, again in the Marina District, mostly in the Marina District of San Francisco. And then, of course, the important point is the difference between these events and the 1995 Kobe earthquake, much more significant earthquake, because this earthquake actually occurred beneath an urban center. Neither of these two earthquakes occurred directly beneath an urban center. So when we think about the kind of earthquake we need to be ready for, it's Kobe. It's not Northridge or Loma Prieta. Northridge and Loma Prieta were getting off relatively light, just like the Napa earthquake earlier this year, and that was also not a major damaging earthquake. So what we have to recognize is that the reality of today's vulnerabilities. Hurricane Katrina was a real eye-opener for many people in the United States because people didn't believe that you could do such widespread damage to a modern, wealthy city. 50% of the population left New Orleans as a result of this event. Many of them, or some of them, came back, but the population is still not back up to the population that they had before the event. Of course, this is not an earthquake, this is a hurricane, but it illustrates that we are sensitive to these kinds of impacts. Yeah. So the question here was, in the past midterms, I've not really emphasized needing to know dates, and is that something that you guys will need to know for the final? So no, I mean, my emphasis with all of the exams is not on remembering specific numbers. It's having a general sense. So the example I like to give is when we talk about the Loma Prieta earthquake and the Northridge earthquake, I expect you to know that it was about 60 people that died in those two earthquakes, as opposed to 6 or 600. That's the kind of thing. I'm not going to expect you to know that it was 56 in the case of Loma Prieta. I'm not even sure if it was. I made that up. Okay, so today's vulnerabilities. Hurricane Katrina showed that there really are these vulnerabilities, and as I was just saying, the Kobe earthquake is the kind of event that we need to be ready for, both here in Northern California and also in Southern California, and just some images that you've seen before from that particular earthquake. Okay, we then talked about earthquake science, and we started off by talking about faults, which of course are where earthquakes occur. We talked about Wallace Creek and the geomorphology of Wallace Creek and how we can use that geomorphology to understand the history, the long-term history over hundreds of years, even thousands of years, of motion on the San Andreas Fault. We talked about the Alpes Preola earthquake fault zones, and in particular the Hayward fault zone closer to home. Here's the stadium, bang on top of the Hayward fault. And then we looked at other faults and the impacts, the local effects of motion on these faults around the world. This particular example is from the C20 earthquake, which was, of course, a thrust fault. In California, we're expecting we have strike-slip faults. This was a thrust fault, which is why you have this vertical offset that was caused by the C20 earthquake. Okay, we then talked about earthquakes themselves. We talked about the earthquake cycle, the elastic rebound, somebody mentioned a few minutes ago. And so that's the process of building up towards an earthquake, what was actually termed the tectonic time bomb by one of my colleagues a few years ago, indicating the fact that, every single day we are getting closer to a major damaging earthquake on these plate boundaries. There's no getting away from the inevitability of these large magnitude earthquakes. And we looked at the history of faults or earthquakes on other faults where we have longer histories than we have in San Francisco. Specifically, we talked about the North Anatolian fault and the fact that there's been this progression of earthquakes from east to west going down the North Anatolian fault, the last one being Izmit, and the realities of what this means for Istanbul over the course of the coming few years. We talked in more details about how we extract information about these earthquakes. This is the rupture pattern for the Northridge earthquake beneath Los Angeles, beneath the San Fernando Valley. And so if you remember, that was also a thrust fault because it's in the big bend of the San Andreas fault. There actually is some collision tectonics that are going on, and as a result of that, you have these thrust faults. This was a blind thrust, so we didn't know about this fault until the Northridge earthquake occurred. The rupture itself initiated relatively deep on the fault, which is at, can't read that, at 19. So this is at about 18 kilometers depth, and it ruptured up across the fault plane up towards the surface until 6 or 7 kilometers depth. And this is the time history of that rupture, starting deep on the fault and migrating diagonally across the fault plane up towards the surface over the course of about 6 or 7 seconds. Okay, so the earthquakes like this, it takes time for the rupture to make its way across the fault plane. Bigger earthquakes take even longer than this Northridge example. Yeah. That's a great question. So the question was, the rupture took, let's say, 6 seconds. So does that mean that people felt shaking for 6 seconds? What's that relationship? So first of all, of course, people only start to feel any kind of shaking once the seismic waves have reached them. So in fact, that was the other thing on here. So here's a typical seismogram with the P wave arriving and then the S wave arriving. So this energy here, the P wave and the S wave, is being generated by the entire fault plane. So if it takes 6 seconds for the rupture to go across this fault plane, that means that there's at least 6 seconds worth of P waves that arise at any given location, and at least 6 seconds of S waves that arrive, because P waves and S waves radiate from the hypercenter right here, and they radiate from every point, including the last point up here to slip. Okay, so that means that you have at least 6 seconds of rupture. But in fact, you have longer periods of rupture. This seismogram isn't from this particular event, but you have longer periods of rupture because this energy is bouncing around within the Earth's crust. So the actual duration of rupture is always longer than the duration of the event itself. And as events get bigger, the duration gets longer, there's more energy, it bounces around for longer, and so the duration gets even longer. Okay? So we're talking about several minutes worth of shaking in the case of the magnitude 9, the Hakuoki earthquake, for example. Okay? Any other questions? Okay, and then we talked about earthquake effects. There are three key sort of earthquake effects to think about. The first is the fault displacement itself. And so here's an example of an offset road. This is from the San Fernando earthquake in southern California, and a road that happened to go directly across the fault, as you can see. If you have a building that is right on top of the fault, you have to worry about what it's going to do to the building. It can literally tear the building in two. Although at the same time, if the building is strong enough, you actually see the surface deformation go around the building. As in the building is cohesive enough, it stays as a single unit, and the fault can go around it. Of course, you don't want to be relying on that, but that's what we actually see. Ground shaking, excuse me. Ground shaking is perhaps the biggest hazard in the sense that it affects the widest area. Okay? And so most of the damage is usually due to ground shaking kinds of damage, and that's just because the ground shaking extends over a very wide area. And then the third category is liquefaction. Again, this can be very serious. There's kind of almost amusing examples here where entire apartment buildings are sort of rotated onto their backs as a result of losing cohesion of the soils that these buildings have been built on. Usually, of course, the buildings actually collapse. These are obviously very strong buildings who have not collapsed while they were going through this rotation. And so liquefaction, of course, occurs in regions where we have soft sediments, often fluid-saturated sediments. That's the kind of locations that you get liquefaction effects. Okay, and then finally, earthquake preparedness. We talked about earthquake prediction. We've already covered the fact that not only can animals not predict earthquakes, nobody can predict earthquakes, in fact. So we're not able to predict earthquakes. What we can do is we can forecast earthquakes, and this is really the key piece. By forecasting the likelihood of earthquakes, and that includes not only the likelihood that we will have an earthquake, but also the ground shaking that we can expect, the distribution of ground shaking that we can expect from that earthquake. That allows us to come up with maps like this that show probabilistic ground shaking. So this is the actual earthquake probabilities, the ground shaking probabilities, and then we feed that directly into our building codes. So buildings are built so that they should withstand the kind of ground shaking that we expect. Okay? So this is the key piece. This is what means that most buildings in California are not going to collapse on you in an earthquake. Okay? Buildings that have been built to modern standards. And then, of course, the new piece here, the icing on the cake, if you like, is earthquake early warning. The fact that there's this additional layer, or there could be this additional layer of protection in that you get a few seconds warning, and that allows you to take some additional final measures to reduce the impacts of the earthquake. Okay, so that's kind of the overview of the entire class. Now I want to talk about how individuals make a difference. How do you make a difference? How do we as individuals, we as an institution, actually prevent fatalities in the next earthquake? And so I'm going to start with UC Berkeley. You've heard me give UC Berkeley credit for its earthquake retrofit program. That retrofit program all started in 1997 with what was called the SAFER Review, where they went across campus and they looked at every building and they identified the seismic safety of all of the buildings on campus. And the conclusion was that 27% of campus space rated as poor or very poor. Okay? So this is not good. This meant that it was likely, doesn't necessarily mean it was going to collapse, but it means that these buildings were not going to be usable after an earthquake at all. Okay? 27% of campus space. So that has very serious implications for the ability of campus to survive. Okay? If we have an earthquake, obviously a serious earthquake, campus will close down, perhaps for a semester, perhaps for 2 semesters. When it comes to students, so that would be you guys. You may take a semester off. You may take 2 semesters off. Some of you might transfer to other colleges. But then there would also be new students who would come back after a year or 2 years. The challenge here is the research element of campus. This is a research university, as you know. All of the faculty here are equally engaged in research and teaching activities. Research grants would not go away. They would continue to exist. And so it would be up to faculty like myself to continue that research effort. If that's not possible, then it's going to be very difficult to stay at Berkeley. So many of the faculty would likely also move away while campus was getting itself back on its feet. And the likelihood that they would come back once they've set up their research programs at other institutions is low. And that was the factor that meant campus decided to invest in seismic retrofit for the continuity of campus activities and the very survival of UC Berkeley as a whole. So at that time, it was estimated that it would be $700 million to retrofit campus. And so they decided to embark on a 20 to 30-year program to retrofit all of the buildings on campus. It's an ongoing program. The costs sort of then started to escalate, as they always do, $1.2 billion. I believe right now campus has spent more than $2 billion retrofitting its campus for earthquake safety, which is quite an astounding thing to do. It's worth noting at this time that they had already started to retrofit the residence halls. So the residence halls are a key piece, of course, because you guys spend a significant fraction of your time in the residence halls. And so the residence halls were already being retrofitted at the time that they were doing this safety program. And so today, I say today, this map is actually from November 2005. So it's pretty old. I can't get a more up-to-date version of the map. This is all I have. But even in November 2005, you can see that most of the buildings, the green buildings here had already been retrofit. The blue buildings were underway at that point. The stadium, of course, has now been done. And the red buildings were still on the list. We talked a lot about Evans. This is Evans Hall. It is still on the list. So there's still more to be done. But the point is that a lot of progress has been made here on the Berkeley campus. And this is where the role of individuals is really key. So how did that happen? How did we get to the point where Berkeley has spent $2 billion retrofitting its buildings? Well, Mary Camiro, who's a professor in the architecture department, is largely responsible for this. Okay, obviously, she didn't do this alone, but she initiated this whole effort by looking at the economic benefits of disaster resistance at the university. So you have to make an economic argument. To get people's attention, there has to be dollars behind it. And she argued as to what the economic impact of a big earthquake on UC Berkeley was going to be. She made the case that I just laid out to you about research moving elsewhere and not coming back and the long-term impact that would have on the institution. And then with colleagues on the UC Berkeley Seismic Review Committee, which is a committee of faculty that review these things, they made the case to campus administration that this was really important and that they should initiate the retrofit. And obviously they did. Okay? So again, it's individuals who identify what the problem is, make the arguments as to why it's important to make changes and to make these improvements. Those individuals make all the difference. Another example of an individual that made a huge difference, this time to the city of Berkeley, is Arietta Charcos. Arietta was a city official. She worked for the city of Berkeley. She had kids in the Berkeley schools, and she recognized that the Berkeley schools